Section 1.2, functions and their properties. This is like the most important section of the year.
Basically, what she said.
Okay, starting off, a blank is a set of pairs of input and output values.
Coordinates.
No, relation.
Oh.
A relation.
Like
a relationship.
Because there's two of them.
Because there's, it's a relation is something that puts these values with these values in like an organized way.
Right.
They can be represented in numerous ways. You can do ordered pairs, like a list of ordered pairs. You'd use a squiggly bracket at the beginning of that.
Okay.
And we could just have like
a fancy bracket. Those are what the squigglies are called.
You just could have like some random set of ordered pairs or whatever, like this.
Wow, that's a bunch of ordered pairs.
Or I'm gonna do one more. We could have like maybe this. Okay.
Ooh.
Okay. So
some ordered pairs.
So write down those examples of ordered pairs.
No rules, just right.
Right. Input output table would be like your XY table.
T charts or things of that sort of nature.
And they can be vertical
or horizontal. By the way, we don't know what these graph. These are just
we're just
making
picking
these
stuff up.
Yep.
Yeah. Straight from my mind into the pin, through the cord into the computer.
Instantaneously, almost.
Almost.
So there you go. There's input output table. You put the X in.
Jot that down.
You put the X in. You get the Y out.
Hey, that sounds like a song. Okay, a coordinate plane. It could actually be just like an X and a Y, and then you could have like some random points.
Hey, those random points are linear.
Those are. That is kind of a linear fashion. Or you could actually have a graph, and so maybe your graph looks like these.
Hey, that looks like a quadratic.
That does look like a quadratic. That's totally what I was going for. Or you could have a graph maybe that looks like this.
That looks like a conic section.
Okay, well, like a circle or an ellipse.
Yeah.
Okay, and then mapping diagram is the one that we'll see the least and has more application in like super obscure levels of higher math. But
she would know.
Yeah, you've got two circles, an input and an output circle, and you have numbers in each.
And they just draw a line into the output circle draws to the input draws to the output. So there you go. That means 1 goes with 4, 2 goes with 4, and 3 goes with 5.
Right.
Yeah.
Okay, so
all right.
Now that we've got all these different ways of representing relations, there are specific kind of relations that we really care about.
Okay.
And they are called functions.
You know what? We're going to study functions pretty much until we study conic sections.
And then they're not functions, they're relations.
Those aren't. Those are just relations.
A function is a relation where every input has exactly one output. That means if you put in a number, you only get one answer. You don't get more than one answer.
You can't get more than one answer. So if I put 1 in, I'll get a 2.
Or whatever it is.
Or a 3. But if I put a 1 in and get a 2, and then I put a 1 in and get a -2, no deal.
Right.
That is not a function.
That's not a function. So on this first example, we're actually going to determine which of these above, which is why there's multiple examples up here, we're going to determine which of these are functions, and then also we're going to look at these 2 equations down here.
Okay, let's do it.
So when we're looking at ordered pairs, what matters is that if each input has one output, my x values better not repeat.
Yeah, you can't have any x values over and over again. That's no deal.
So this first one, 1, 2, 4, we're fine. It didn't
Sounds
repeat,
good.
so that's a function. Okay, but for this second one, 0,
zero
has
is,
2 different things for y values.
It could
so
be
that's
1 or
not.
3, so that's no deal.
Absolutely. For our input and output table, again, we really just care about our x values. All of our x values are different here. It doesn't matter that our y's are the same. This is a function.
That's a function there. The other one is not, because -3 gets used more than once.
And goes to different things.
And it goes to different numbers. Now, if you had -3 go to 5 or -3 go to 9 several times, that's different, because that's an individual
like
point.
if I had made this a 5,
right.
That's just the same point repeated. So that would have been fine. On the coordinate plane, we have a special test that we do, and I'll write it up here.
Vertical line test.
Yes, a vertical line.
It's quite handy.
Is the line that goes up and down. And
Vertically.
Yes, the vertical line test says that if I draw a line anywhere on my graph, as long as it goes through the graph once, then it's a function. If anywhere it would go through more than once, I've got a problem.
Yes.
So because these points are all lined up differently, this would be a function. Like if I had a point right on top of each other, like another point here.
Well, that looks danger.
Yeah, that wouldn't work. Okay, but for these actual graphs here now,
That's
like,
a function. Quadratics are functions.
Yep, because it only goes through once no matter where I draw it. But
That's
here,
not a function.
That's not a function.
Because notice it's going to cross that circle. Now, Mrs. Stevenson could have drawn her line way over on. Draw a line right there on one of those. Yes, right there.
I could draw a line there. It
only goes through once. But we have to be able to draw that line anywhere on that graph.
Anywhere
on that graph, and
Right.
only touch it once.
Right. So that's the vertical line test, which that should seem familiar,
Right.
I believe. Mapping diagram, you're looking for each input needs to go to only one thing. So this is a function because all the arrows are good. But if we had, I'm going to go with like a simple scenario here. If this one was going to all of these things, that's not a function.
Bad. That's bad.
That's bad.
All right.
So how can we tell just from looking at equations? Because we could graph these.
We could graph those.
Especially this first one, a square root graph. I don't know exactly where it is off the top of my head, but I feel like it's something like this.
Yes, I would agree that.
So vertical line testing that would prove that this is a function.
Right.
Okay, but what actually happens is there's only two cases that I know of that really screw with us as far as function or not a function, and that's y squared or absolute value of y.
Okay, sounds good to me.
Because,
so don't screw with those.
Because if I try to put this in my calculator, I have to solve for y.
Right.
So I got to subtract x squared over y squared equals 9 minus x squared.
And then when you take the square root of both sides,
you know what you got to do?
You got to have plus or minus the square root.
You gotta.
And now that tells us that y could be two different things.
Right.
And that's
what we mean by you put in an input to x, but you get two answers out.
Right. That's no deal.
That's not a function.
Yeah. So anytime you have y squared or absolute value, and pretty much really that is the only sort
those
of
are the
situations.
only two I can think of.
Yeah.
If you see those situations,
Run
like
away.
absolute value of x is fine.
Right.
But in both of those cases, think, how do I put that in my calculator?
Right.
And when you're like, ooh, that's rough.
Or think, how do I get y to be all alone?
Yeah, how do I get y to be alone? Especially the absolute value, that's
Right.
tricky.
Yeah, because that's
We don't
negative
really
y, positive y.
Yeah, we don't talk about that a whole lot usually. And actually, I thought of another example. X equals any kind of number is a vertical line. And that
Oh,
wouldn't
yeah,
be
that's not a function either. Okay, yeah.
So there's our non-functions.
Okay. Hey, domain and ranga.
Domain and range. Domain is the set of x values for which a function is defined, and range is the set of y values for which a function is defined. So it's the idea that we have a certain set of numbers
Right.
that we can put into a function.
Okay.
Okay. And then we get out another set of numbers, and
Right.
that's what the domain and range is. Most functions have a domain of all real numbers, which we would put in interval notation as negative infinity.
Interval
comma, positive
notation you maybe
infinity.
have not seen a lot
we're-
of, but
We're going to go over it like...
yeah, and interval notation is super handy.
Yes, it is like the best way.
Are you playing Clash of Clans?
I just wanted to grab my
Are
minerals.
you?
Because, and the reason it's negative infinity to positive infinity is because you can plug any number into whatever equation
Right.
you have and get an answer out.
any number.
And that's like
You pay,
a line.
57 million.
You can put it in and get it, an answer for it.
Negative 238,327 jillion trillion.
You can put it in and you can get an answer for that.
There you go.
The two main times our domain is not all real numbers, especially initially here, involves fractions and square roots.
Those are the two biggies. In fact, in all of math, those are the two biggies that when you run into domain issues.
Yes.
So, because what number can you never, ever, ever have in the denominator?
A zero.
You can't have a zero.
You cannot divide by zero.
Can't divide by zero. Now, I could put a zero in that denominator.
Yes, 0 plus 3 and
is
get an
3.
answer.
But I can't put negative 3 into that denominator.
Right. The idea is you take your denominator and set it equal to 0 and
Right.
you solve. And if that's the only issue, we just have a fraction, we don't also have a square root, then the only number we can't plug in is negative 3.
That's it.
So how do I write that in interval
Well,
notation?
you would go from negative infinity up to 3, but you can't include the 3. So we're going to use parentheses. And then we're going to do the little union hoochie coochie.
Symbol.
And then we're going to go from negative 3 to infinity. Now, what was just written with these parentheses around negative 3 says you cannot include the negative 3.
Right, we're saying it's
can't-
not equal to
so
negative
It's not
3.
equal to negative 3, but you can go up to negative 3, but you can't include it because we have to have a way to symbolize mathematically so close to negative 3 you can basically touch it without touching it.
Right. Totally. Agreed.
Okay.
And that's how we do it.
That's it.
So brackets here would be totally inappropriate.
Right, because brackets now say we are actually going to include the -3 in our solution set. And that's no deal on this particular guy.
Right. Now, you viewing at home, plug this in, y equals 2 divided by x plus 3, and make sure that unless you have a fraction button, you're putting the parentheses around the bottom. And if you graph this, it should look like, hang on one sec, I got this. I'm thinking this right here.
I'm thinking you're right.
Okay, it's a reciprocal
Should be ishy.
function, something
Really
like
close
this.
to that.
There should be asymptotes at -3 and at 0. So that confirms -3 was our issue, because
Right.
that's where we have a break in our graph. But also to find our range, typically, unless you're just super good at thinking about it in your head.
You need to see a graph to get range.
Right, and so the issue with our range, we've got all these values here towards -infinity, all of them up towards positive. The only issue is here with this asymptote at 0.
Right.
So we're going to use interval notation again, but this time 0 is the value that gets excluded.
And we can't include 0 in this point because our graph...
It goes right up to it, and I didn't do a great job of graphing that to show that. It gets right up to the line, but it doesn't touch it.
It doesn't touch the line at all. In fact, think about a large number that you could put in for x on that problem, like 700.
Yeah, it would get really, really close to 0.
Really small,
but it's not 0. Okay, the square root of x minus 6. What's the issue with square roots?
Okay, the issue with square roots is, for now,
right,
we don't know how to deal with a negative square root. We're going to learn.
Yeah, and we'll have imaginary numbers, but even when we talk about graphing, you still have an issue.
That's right.
Because you can't graph an imaginary number.
You can't graph an imaginary number. So
not exactly.
We have to make sure that everything we get under the radical is equal to or bigger than 0.
Right. Okay, because we don't want negatives underneath our square root. So if you'll set up this inequality, and if something really tricky is underneath that square root, this may you may have to be tricky back.
Yeah, you may have to be super vigilant.
But if it's simple, hey, x has to be greater than or equal to 6.
That's all there is to it.
Now, how do I write that in interval notation?
Well, you're just going to go from the actual number -6. So that's a positive 6. So that's a bracket because the 6 is now actually included. Listen. I can take the square root of 0, and don't forget that, because you will.
Okay, the square root of 0 is 0,
and then you
so
go all
that's
the way
why
up
we're
to
equal
infinity.
to.
Yep.
And we can go all the way to positive infinity. Now, if you'll put this in your graph as y equals square root of x minus 6, you should get a graph that looks like this.
Yes.
Where, and you might look at your table of values to help. You should have errors.
It's going to say
way,
errors, or it might be blank.
Right, and it should start, this point should be 6, 0.
Right.
And so that confirms our domain that we started at 6 and we went to the right. And our range, the lowest value we have for y here
is 0.
And
so notice that our graph here goes up kind of slow.
But that doesn't matter, because if we could go forever, we'd still get to infinity.
That's right.
And remember, infinity never gets a bracket because you can't be equal to infinity.
You can't, yeah.
It's just an idea.
Give me a number for infinity. You can't do it. It's not possible. Because every number you give me, I can just one-up you.
Right, totally. I agree. A function is
continuous
if there are no breaks in the graph between the start and stop of the domain. And actually, I think I just told you the answer, but I meant continuous on its domain.
Oh, it's continuous on its domain.
Yeah.
I'm going to finish my cheese, Bob.
Okay.
Because I was in mid-chew.
Sorry. Okay, what we mean whenever we say on its domain is that
where the domain is defined.
Yeah, where the graph is, it is continuous. So here's some situations we could have. We could have continuous at all x. So look, it's nice, and I could trace that without picking up my pencil. That's a key thing.
That's the key thing. If you have to pick your pencil up at any point in time, it's not continuous anymore.
Right. When it's not continuous, we call the places it's not continuous discontinuous.
Oh, because it's not continuous there.
Right.
It's discontinuous.
Yes, like when you have a disagreement, you're not agreeing.
What?
Nothing. So on this one, when we get right here at this open circle, we'd have to pick up our pencil and draw that dot. So it's discontinuous. We call that a removable discontinuity because, and I remember it this way, I could just fill that in and it'd be continuous.
Right.
That's a removable discontinuity.
Yeah, if you can just do one little dot, if you can just boop, and you're done, it's removable.
Right.
If you gotta like do some other stuff and start sketching and shading,
then that's not gonna work.
No deal.
So another kind of removable discontinuity on the second graph.
Well, now let's talk about this for just 1 second. This second graph right here. Notice it's defined at every point that we see.
Because even at this point A, we've got a value there.
We've got a y value. If I go, what's the value of A? You can tell me.
It's this one right here.
All right, but if we go to that middle graph, this one,
there is no value.
There's nothing. There's a hole there.
Yes.
It's like a hole.
So that's the difference between those two graphs. This is still discontinuous, and it's still a removable discontinuity because I could still just, and then it wouldn't be discontinuous. Okay, but they are slightly different on this.
It's a little bit different. Yep.
The next two we've got are jump, because our graph jumps. If I'm tracing, all of a sudden I have to pick up my pencil and make it jump up here and keep going. That's not removable.
I always think of a ski jump too when I think of that.
Because you'd have to like draw a vertical line, and that's not a function.
No, that's more than just a little. You gotta start like.
And even if it was shifted over and I was drawing a line like over this way, like you can't do that.
Not removable.
Not removable.
Yeah, if it's not a little, then it's
not.
It's not removable. So both of these aren't, because and there's no like heartbeat situation like on this one trying to connect the bottom to the top and
some of your calculators may try to do that when you graph.
That's not how it goes.
There's supposed to be asymptotes there.
Yeah, if you draw a heartbeat situation like this, a puppy dies. I mean, that's just how it happens.
This is, I think, what he's referring to by a heartbeat, right?
Yeah.
Something like that.
Yeah, that's not it. Don't give us that.
Okay, so let's do an example.
Okay, let's do it.
Graph the function and tell whether or not it has a point of discontinuity at x equals -1.
You have a calculator?
I don't. I'm sure you do. If there is discontinuity, tell whether it's removable or non-removable. So,
I happen to have a calculator. Right?
Well, that's great. When we graph this on our calculator, the thing is because it's specifically asking us at x equals -1, once you graph it, check the table of values.
That's a great idea.
1.
That is a great idea. Always check the table of values. Very important.
So Hazelwood is typing that in.
I'm x plus 1ing.
Mm-hmm.
I'm x squareding.
Do you know the bottom of this factors?
Shut the door.
I thought you liked the door open. You want me to go walk over there and open it? I mean, close it?
I don't know. Does it factor? But the top doesn't factor out, does it?
The top is x plus 1.
I feel like then my graph doesn't match what you got.
No, it does. It does. So we've got like
Shouldn't
this
it be
asymptotic
it should be 1
thing.
over. Okay, all right, we're good. Yeah.
Okay, so on his graph, what he's seeing, and this is what threw him off, was that over here at like 3, we've got an asymptote, right?
And I was expecting a straight line.
Yeah, but it's not a straight line. But what matters is not that asymptote at 3 or whatever it is. We care about what's happening at -1.
And I didn't see the asymptote there. But that's because it's a hole.
Right. So at -1, I don't know what it is exactly, but there should be a hole here. If you look at your table of values.
Yeah, and if you look at your graph, you're not going to see that hole.
No, you're not.
Your calculator has to string all those points together.
But you should have -2 should have an answer. -1, it should say error.
Table of points.
0.
Undefined at -1.
Should say it should have a number. So you're looking for, that's a hole right there.
Yep.
It is not defined there. Now here's let me throw this out here. The reason that we get removable discontinuities like a hole is because if you factor the bottom, you can cancel out the issue.
Right.
Okay, and so that gives us 1 over x minus 3. This right here without that hole is the graph of 1 over x minus 3, but just because I could cancel it out doesn't mean that I don't still have that original issue.
We still have that problem.
We still have it. So a removable discontinuity is when you cancel stuff out.
Right.
Okay, a non-removable is the things left over.
Right. I agree with what you just said.
Cool. Relative extrema,
shoot.
increasing, decreasing, and constant. So relative extrema is the plural of, cut it out, extremum, which is just a fancy word for maximums and minimums.
Right. Extrema just means where you have a peak or a valley on your y coordinates.
Right.
So. And
we are looking at what's called relative or local.
Global.
Global is not what we want. Isn't that all of?
That's the chief daddy big and.
But we don't want.
Okay, all right.
no, we want local.
Local it is.
Relative and local, because a relative or a local maximum is all the places where we switch from increasing to decreasing, and a relative or local minimum is where we switch from decreasing to increasing.
That's right, peaks and valleys.
A graph is increasing when it is rising from left to
but
right.
I have one you can borrow. Okay.
Decreasing when it is falling from left to right, and constant when it's not going up or down from left to right. So we read graphs from left to right just like you read letters, right?
In English.
In English, yes. Specifically in English, we read from left to right. So if I start over here and I start going this way, am I going up or down?
You're going up.
Okay, and I go up the whole time?
It looks that way.
So this is increasing. It's an increasing function, and it's actually, we again use interval notation for this. It's increasing the whole time.
What x coordinates does it increase?
Right, we only care about the x coordinates when we talk about this. Here, if I start here, I'm going down
Falling
the whole time.
Which means you're decreasing.
This one, what am I doing?
Pretty much you're constant.
Yeah, because if I go from left to right, I'm not going up or down.
Not going up or down at all.
The whole time. And this last one has all three.
Oh.
So from left to right.
Okay, here we go. Left to right. From negative infinity to, is that a negative 2?
I think it is. It is kind of tiny on there.
You're decreasing from negative infinity to negative 2. Now,
we have kind of a disagreement.
We have a professional disagreement with exactly how you should notate this. So because of that, you can notate
either way.
Either way.
And it's the math community
in general
realizes that both of these things are true.
Right.
You can either put it with parentheses.
Why did you put yours first?
Or brackets, because mine's better. Mine's more right. Because you could say that it's decreasing all the way to negative 2, and you could include that because we don't have a hole there, and that would be a bracket. Or you could just use parentheses the entire time you're doing increasing, decreasing, or constant, which is what I like to do. Because are we really decreasing at a point where they switch?
Yes,
No.
all the way to that point of negative 2, and then you change. Ludicrous, her thoughts.
We are constant from negative 2 to positive 2, and again, you could do that with parentheses.
Why do you put
Or
parentheses first? What about
with
my
bracket.
way first? I'm going to take the writer from you.
After this problem, be my guest. And then from 2 to positive infinity, we switch to increasing. I just want them to be consistent. Okay? Do it one way or the other, but don't combine them.
Yeah, combining is bad. Be consistent in your beliefs.
Now, if you ever did have a situation where there was an open circle here, you would have to put parentheses.
Right, yeah.
Because it's not equal to there.
The only reason that there's disagreement on this is because we're actually kind of at a corner point.
Right, and so it's the question of, are we really...
we're still defined at that point.
Right,
okay?
But everyone...
has their own opinions on that one. But if you have a hole or an asymptote or a situation where there's a 0 in the denominator, those cannot be included. They just cannot be included at all.
Right. So we already talked about this paragraph. Relative extreme refer to the extreme points of our graph, known as relative maximums and relative minimums, and how it switches. So let's graph this function, and we're going to find all the relative extrema, also known as local, and we'll also go ahead and identify the intervals on which the function is increasing, decreasing, or constant. Those two things kind of go hand in hand. If we're asked increasing, decreasing, or constant, but not asked to find the maxes and mins, we're still going to end up finding them to figure out where the point is that they switch.
So, is that a cubed?
Yes. I happen to know this will have a max and a min. And it has part of the time increasing, part of the time decreasing. The only time you get constant functions when you're plugging in actual functions is if you've got really weird absolute value or some kind of piecewise situation. So here's what it should look something like this. So we need to find those points. Is that good enough?
I feel like that's probably appropriate.
Because, and the only reason I'm even sketching it is because we need to find this point, which it's not really 0, 1, even though it kind of looks like that on mine right here. But we need to figure out what this is. That's our max. And on your graph, you go to, or on your calculator, you go second trace maximum. You got to do a lower bound or a left bound and an upper bound or a right bound and then guess.
And if you have Inspire, you go to Menu, Analyze, and then you pick it.
Right. So what's our max?
Our max is going to be 1.1. And I'm sorry. The X coordinate is negative 0.22. My mistake.
So wait, what's the point?
The point is negative 0.22, 1.1.
Okay, and then our minimum?
Efforting that. So, still working and processing, and gosh, then of course it stacked the answers one on top of the other. So 1.5 and negative 1.6. Now you could have a slightly different number on these depending on how far out your decimals go.
Right.
But it shouldn't be too different.
We actually prefer 3, but if
Three
your
is what we
calculator
prefer.
automatically gives you 1 or 2, then we can deal with that. Once we have our maxes and our mins, now we're looking for
increasing, decreasing
and
behavior.
decreasing.
And
so we're starting off increasing until we get to here. Now what's
Right.
important is we care only about the x value.
yes. What values of x is the graph increasing?
So we're going from negative infinity to negative 0.22. And then we actually start increasing again from here up. So from 1.5 to infinity. I could use brackets on these. I just forgot.
You can't use bracket with infinity, but you could use bracket on the negative 0.22 and the 1.5.
Right. And so in between here now, this is decreasing. So between negative 0.22 and 1.5, we are decreasing.
And again, you can use brackets here. So you do have a little bit of freedom in noting on this, mostly because we're defined at everything.
Right.
Which is why we would have the ability to do that should you choose.
If you want to do brackets, do brackets.
That's right. Okay, good.
All right, boundedness.
Oh, this can be tricky.
Yeah, so when we talk about a graph being bounded, we are talking about it having a ceiling and or a floor.
And if
that,
there's a legitimate ceiling that you just can't pound your way through the top then you're bounded.
Right. So our graph can do whatever it wants inside of a ceiling or a floor.
Just can't go past it.
It just can't go past it. And so we have 4 answers possible when they ask if a function is bounded. It can be unbound, meaning that it doesn't have a ceiling or a floor, or not bounded.
Right. So it's unbounded or not bounded, yeah.
Okay.
Unbounded sounds more fun.
Yeah, it does. It sounds like a book.
Yeah.
Unwind, but unbound.
Yeah, we're unbound.
Okay. It could be bounded above.
Deep in the jungles of Afrinor. I don't know, I was making it up as we okay. It could be bounded.
It could be bounded above, it could be bounded below, or it can be bounded above and below, which you could just say bounded for.
Yeah.
Okay, so we've got 4 graphs here. I bet we'll have 4 these will match up.
I bet you're right. So
does this have either a ceiling or a floor?
Well, it looks like it's going through the floor.
It
because
does.
the graph continues to fall.
I can get to negative infinity for y, so it's not bounded below, but I cannot
looks like I can't get up to 7.
I can't. Yeah, whatever this is, it's stopping us, and so
That's
this
the ceiling.
is bounded above. All right, next.
Next one now. This one we're actually pointed towards infinity on the top, so that would tell me that
It's
go
not
through
bounded
the
above,
ceiling,
but
and
this looks like an asymptote down here
it does.
preventing us.
Ask myself, does that graph get near the y coordinate of -6?
No, it doesn't. It doesn't. It doesn't
Indeed.
go anywhere near it. So,
So
it's bounded below. Now this is a sine curve.
Oh,
which
I happen to know a thing or two about sine curves.
So do I.
So
it's almost like we teach trig, which has to do with sine curves.
yeah. For your information, the sine curve will never go above -1 or below 1. Your sine curve will never go above 1 or below -1. So it has a floor and a ceiling.
So that means it's bounded.
It's bounded.
And you'll also see the book say bounded on its domain,
right?
Which means the same thing as what we've been saying, that it's bounded for where it's defined.
Right.
How about this one? Oh,
well,
look, ceiling and floor.
Oh, can you get?
Wait,
Can you get?
we're
no,
going
we gotta
through
go. Yep.
to infinity and negative infinity.
You almost faked me out there, but I'm on to your slick ways.
So this is unbound or not bounded.
Not bounded. Yeah, unbound. Deep in the jungles of Afrinor.
There you have it. That's bounded. Symmetry.
Indeed.
There are 3 types of symmetry that we are mainly interested in. Symmetry with respect to the y-axis, the x-axis, or the origin.
Now, the x and y-axis are most easy to recognize in my opinion.
Because it's like a hot dog or a hamburger fold situation.
Right. When you're dealing with the origin, it's most handy to have a calculator, because if you're symmetric about the origin, if you look at your calculator this way and see the graph, and turn your calculator upside down and see the graph, it should be the exact same.
Or another way of looking at it is whatever is over here in my first quadrant, it should be the same in my third, like rotated around and in my third.
Right. Like actually spun around.
Yeah, and like this should be the same. Whatever's in 4 and 2, those should be the same.
Right.
All right, so graphs with symmetry with respect to the y-axis are called even functions.
Yes.
And it actually has to do with this handy thing where if all of your exponents for your variables are even, it's an even function.
Hey, how about that?
The way you test for symmetry is replace x with negative x, simplify.
Now, this sounds like a really weird thing, but just follow along with the rules here, okay?
Replace x with negative x.
That means that we're going to take, in parentheses, negative x and square it.
Well, wait, negative x squared is just
x squared, because a negative times a negative is a positive.
So what we end up with is what we originally had. That makes the function even.
Right.
Now there are some other ones that you can't use the exponent trick for, like if we had absolute value of x, is that an even function? Of course it is, because when I plug in a negative x into my absolute value bars, well, the absolute value of a negative number becomes a positive number.
So that's even.
But that's algebraically, if it asks for it, that's what we do, is we plug in a negative x and see what happens. Graphs with symmetry with respect to the x-axis are not functions, so we don't really care about them so much. Like, for the most part, we'll be dealing with functions.
Right.
And because this would be a situation where we've got like a parabola on its side.
Right.
It does have symmetry across the x-axis, but it's not a function. It doesn't pass the vertical line test.
But we'll talk about some other graphs later, polar coordinates and some things like that, or tangents. Some of those have symmetry this way, don't they?
No.
Oh.
Not if they're functions. Not until we get to conic sections.
Polar coordinates.
And polar coordinates. Okay. Yes. Okay.
All right, good talk.
Okay. Graphs with symmetry with respect to the origin are called odd. See how we've got it to the third power, and that's an odd number. And so for this test, you replace x with negative x, and what should happen is you should end up with the opposite of what you started with. So negative x, when I cube it, is...
That's going to be negative x times negative x times negative x.
Which is negative x cubed. That's exactly opposite of what we started with. 100%. So this is an odd function.
And so if you're checking a little bit of a more complicated function for oddness, everything has to be opposite, not just one thing.
Right. And if you look at the graph, which is also helpful, a cubic function goes up to the right, down to the left, and we can do the trick where you think about, if I flip this upside down, is it the same? Yes, it is. This one up here was a parabola, so y-axis symmetry, for sure. Asymptotes and in behavior.
So asymptotes, we've kind of addressed a little bit.
They are like invisible lines that a graph approaches but never touches or crosses, or rarely approaches.
Rarely crosses.
Rarely crosses.
Yeah, but always approaches.
Yes. Vertical asymptotes never get crossed.
Never.
Horizontal asymptotes are only really asymptotes out at your end behavior. So what's happening really far to the left, what's happening really far to the right.
And really far means bigger than the numbers on your graph or screen. Like really, really.
A lot of times, though, you'll see
a tendency.
It start to get there.
Right.
So if I wanted to find horizontal or vertical asymptotes, then I could graph this.
Right.
And I could look at that. I do know where my vertical asymptotes are by setting the bottom equal to 0. Could you put this in and graph this?
Yes.
Okay,
we're
thanks.
Doing it right now.
Yeah, we're doing it right now. So if I set the bottom equal to 0 and solve, that tells me that there is a vertical asymptote at x equals 1.
Is that x minus 1?
I meant like a colon there, so I don't have too many equal signs. Now there is a way of figuring out what your horizontal asymptote is, but we'll go into that more in the next chapter or something, right?
About how to find the asymptotes? About
how to find the horizontal asymptotes.
Yes, I believe
so. And so it looks to me like that's at y equals 1.
I think so.
And so you can kind of trace on your graph. If you trace and go really far to the left or to the right, then you'll see you're getting really, really
You can
close
look at your
to
table of
y.
points,
or
too.
the table of points will work
Because it
as
happens
well.
fairly quick.
Right.
Yep.
Describing the end behavior of the graph. We're going to
Oh,
use...
by the way, on this, for the record, I don't mean to
Yes.
interrupt,
No,
but
fine.
nowhere did Mrs. Stevenson take the numerator and set it equal to 0.
Because all that tells us is the x-intercepts.
Is the x-intercept. It does not tell us a domain issue at all. So you'll be tempted, but
You might be.
Just don't.
You might be tempted.
Don't do it.
Now, we are going to start doing end behavior in a very specific way. Back in the day, you may have done like falls to the left, rises to the right, blah, blah, blah.
None of that business.
We're going to do a fancy way. We're going to use limit notation. And we're going to say the limit as x approaches negative infinity. You abbreviate limit with LIM.
Right.
As x goes to negative infinity, what is happening to our function?
Right. What
f of
y
x.
value is the function starting to annoy?
Right. So as I go closer and closer to negative infinity, what am I getting closer and closer to? This asymptote value,
Right.
which was 1.
So now you may be asking, this whole limit business, I don't get it. Well, limits are a little tricky to get. Super duper important
For
in
calculus.
calculus.
So we're kind of introducing you to this idea with this notation.
Right.
The limit, as x goes to positive infinity, then we'd follow our graph this
Right.
way. We'd say, what are we getting closer and closer to on our function? And again, we're getting closer and closer
Right.
to 1.
Think about a limit like you'd play the annoying game with your brother or sister in the backseat of the car. Oh, quit touching me.
I'm not touching you.
Oh, quit
I'm not
touching me.
you.
That's it.
I'm
That's how
getting
it goes.
really close.
Yeah, not touching.
But I'm not touching.
Ugh.
So that's what a limit does, is it's if we could get closer and closer and closer, what would we end up at?
Right.
And if we could keep going forever, in theory, we'd get super close to 1.
But never touch it.
But technically we never touch it.
Right. Okay, good.